Welcome to Dark Core, a dying star enjoying the last moments of its life, a scarlet ball of white-hot plasma whose prominence is lost through a cold vacuum in its agony. Two potent powers are at struggle in its depths. They now force the star to expand to dozens of times its size and make it shrink again, only to flare up with new energy. One of these transformations is going to be the last one, but no one can foretell the exact instance with any certainty. This epic sight could be enjoyed by a space traveler approaching CW Leonis, a pulsating red giant which has been thrashing in a death agony for thousands of years, the first in outer space. CW Leonis, 650 light-years away from the Earth. There lies IRC plus 10216, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin, or about 2,000 degrees Celsius, but due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its solid days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium, slowly settling in the star's center. The helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose masses are close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion where helium nuclei are transformed into carbon. This is a so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass isn't sufficient to hit the next level of nuclear synthesis. As a result, the thermonuclear combustion in the object interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with a luminosity at its peak is 11,300 times brighter than the Sun. With a luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 squared tons of material every year on account of this process, an amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example, carbon dioxide, water, and ammonia to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017. Mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonese's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witness phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and therefore creates scorching hot water vapor. The weakness of this hypothesis lies in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact water accounts for just around a billionth of the star's raw mass. According to today's notions of stellar evolution, being a red giant, CW Leonese is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against the background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shock wave and the mind-boggling temperature in the epic enter will generate new elements that are not to be found in a star's interior. For example, uranium, gold, and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. Thank you for watching Dark Core.